Hello everyone, in this video we are going to be looking at chemical reaction rates. So the first thing, the reaction rate, as it suggests, it's a rate and it's the change in the amount of reactants or the products per unit time. By definition, it is a positive quantity, and if the reaction and the products are present in the same solution, then their mole ratio is going to equal to the molar ratio. So what this means is that, okay, that's C, looking at a reaction, so 2N2O5 becoming 4NO2 and then O2. So the mole ratio is 2 to 4 to 1, right? That is our coefficient. And we know that the molar ratio, so this is the ratio for the molarity. So we know that molarity equals to moles over liters. So if they're in the same solution, that means that their volume of the solution is the same because they're in the same pot. So if they are all dividing it, so if the moles are all dividing by the same number, then the molarity is going to remain the same ratio. So their mole ratio is going to equal to their molar ratio. So the molar ratio is just the ratio in molarity. And then mole ratio is the ratio in moles. So sometimes you'll hear me say it interchangeably. That's just because if they're the same pot, they will be the same. And most of the reactions we will be studying happens in the same pot, like they're in the same beaker. So looking at this, let's look at how we can express the rate. So the rate by definition is a positive quantity. So sometimes you will still see negative and positive in front. And in this case, the negative and positive is indicating whether it is forming or decomposing. And that it's just like the thermodynamic quantities where the positive and negatives indicates the direction of the energy flow. The positive and negative over here doesn't mean that it is going to become a negative quantity. It's just saying that the change in the rate is increasing or decreasing. So just in case you were wondering where those came from. So first, let's start by looking at an example reaction over here. So looking at this reaction, first we can notice that the dinitrogen pentoxide is the reactant. So it is being used up as the reaction proceeds. So you can see that when we are plotting concentration versus time, its concentration is decreasing over time. On the other hand, our nitrogen dioxide and oxygen is the product that is being formed. So when we look at its concentration, we can say its concentration increasing, but they are increasing at a different rate. The NO2 is being produced faster because for every 2 equivalents of N2O5, 4 of the NO2 is being produced and only 1 of the O2 is being produced. That's why the concentration of NO2 is higher than of O2 because there's more being produced per 1 equivalent of the reactant. And again, remember that the rate is defined by the change in concentration over time. So when we are looking at the rate of the formation of O2, so this is O2, we can say that its rate is equal to positive because we are forming O2, change in O2 over time. So remember the delta, it's a Greek letter delta and its meaning is change in. So it's the change in concentration over a period of time. And it is a positive quantity because it is increasing. And over here, we're looking at the change in the concentration of O2. So remember, our brackets is the concentration of. And this is not saying that this rate itself is a positive quantity. But this positive is indicating that O2 is being formed. So just to note that. And, well, rate by definition is a positive quantity, but this positive over there has a different physical meaning than that. And let's look at the other one. So when we are looking at the rate of the decomposition of N2O5, so now we're looking at the decomposition of N2O5, we know that the rate is going to equal to negative. And again, this doesn't mean that the rate itself is negative. It is indicating that our concentration of N2O5 is decreasing. So it is being decomposed as we go. So it's going to be negative change in the concentration of N2O5 divided by change in time. So this, again, the negative sign is representing the concentration of N2O5 decreasing over time. So the concentration is not negative. It's just that in this case, the change in concentration is negative. So just as we are looking at the different signs on the rates, just note that, well, hopefully this is common sense that your concentration cannot be negative. So now let's look at the relative rates. So we want to be able to evaluate the rate of the formation of O2 and the decomposition of N2O5 together. To do that, we can say that, well, for this particular reaction, for the rate of the formation of O2 is equal to the decrease in the rate of formation for N2O5. And then in this case, oops, I actually put this. Okay, so in this case, we can see that the coefficient over here in front, so this number arises from the inverse of their coefficient. So this fraction is the inverse of the coefficient in the balanced chemical equation. And it's for O2, remember, it is 1 over here. That's why it's 1 over 1. And that's why I wrote it this way. Usually, we won't even write it like that. But I want to stress that where this came from. And then, again, the positive and negative sign is not numerical. It does have a physical meaning, indicate how the concentration is changing. So then, we can also re-express this thing as, so this, we can rewrite it, so that way it is 2 positive 2 delta O2 over delta T is equal to negative delta N2O5 concentration over delta T. So basically, we just multiply both sides on this by 2 to get what is at the bottom. And the physical meaning is that the N2O5 is decomposing twice as fast as the O2. So we need to multiply the rate of O2 by 2 in order to make them the same. So let me write that down. So this means that the N2O5 is decomposing twice as fast as the formation of O2. So for every 1 N2O5 that is being used, half of the O2 is produced, so at a given amount of time. And from here, we can apply the same logic to that of NO2, and then we can also write that this whole thing, so this thing, will also equal to, okay, I'm just going to erase these. Is also going to equal to, well, this time we're looking at NO2, right? So it's the fraction, and it's a positive value because NO2 is the product that is being formed. And then the rate of NO2 is the change in the concentration of NO2 over a certain time period. And that is the overall rate how the rate of the reactions for the different species in the reaction are related to each other. So in general, if we have a reaction that is AABB CCDD, so remember this little a is the coefficient, and then big A is the species, then we can write it as, so positive. So over here, A and B are being used up, so it's going to be negative. The fraction of the coefficient, not the fraction, inverse of the coefficient, and then the rate of A, so delta A concentration over time, is equal to, again, we are using up B because B is a reactant. So reactant, the concentration of reactant will be decreasing because we're using them up as we go. Inverse of the coefficient, change in concentration over time. And this is also equal to, so now we are looking at the products. And remember, the products are being formed, so we're going to have a positive number. Inverse the coefficient, so 1 over lowercase c, and then the change in the concentration of uppercase C over time. And this is also going to equal to, again, for D, it's going to be a positive value because we're a product, and then the change in the concentration of D over change in time. So this is how they are all related to each other. So basically, if we can use a mix and match of these combinations to see what the question is asking for. So over here, we're going to go through 3 examples of how we can use those in calculations. And again, please, after a couple ones, hopefully you can pause the video, try it yourself, and then we can come back and walk through them together. The first step in the production of nitric acid is the combustion of ammonia. Write the equation that relates the rates of consumption of the reactants and the rates of formation of the products. In this case, again, we know that the rate is going to equal to the negative change in concentration for the products because they are being consumed as the reaction proceeds. So the 2 rates in this equation for the products is going to be negative because, for the reactants is going to be negative. And then the 4, 5 came from the coefficient because the coefficient basically keeps track of how much things are being used during the reaction. And therefore it in turns will also be reflected in the change in concentration because the ratio persists. And for the products, we are looking at the formations, so their change in concentration will be positive, and then the proportion is also following the coefficients because we are looking at a balanced chemical reaction. So we can see that in this case, it's positive because they are the products that is being produced, and then the fraction in front that keep track of their relative rates came from their coefficient. So again, all these expressions, they are all relative to each other, and we can see that if we think about it, the rate of ammonia being used is going to be the same of nitrogen oxide being produced, because when 4 of them is used, 4 of them is being produced. So when 5 oxygen is being used, 6 water is being produced. Same idea, and that's why we can use the coefficient to express our relative rates. The graph shows that the rate of the decomposition of H2O2 over time, so as is shown over here, based on the data, the instantaneous rate of the decomposition of hydrogen peroxide at T equals to 11.1 hour is determined to be this much. So that means that the rate of the disappearance for hydrogen peroxide is 3.20 times 10 to the negative second molar over hour. What is the instantaneous rate of production for water and oxygen? Looking at this one, we can basically start by writing the rate expression. So we know that the rate is going to equal to 1/2 of the change of concentration of hydrogen peroxide over a given period of time. And this 2 comes from here. The negative is because that it is a reactant and therefore the concentration of it is decreasing. And this is equal to positive 1/2 of the concentration of H2O over a given period of time. Again, the 1/2 comes from the fact that we have a coefficient 2, and it's positive because H2O is being produced over time. So the rate of disappearing of the hydrogen peroxide is the same as the production of water because they used up 2 at a given time. And this is also equal to the production of 1/1. Again, this 1 came from the coefficient 1 that was omitted for the concentration of O2 over a certain amount of time. And this is just showing that we have to use up 2 hydrogen peroxide in order to produce 1 oxygen. And therefore, the rate of production for oxygen is twice as much as is half of that for the rate of the decomposition of hydrogen peroxide. So from here, we know that the rate of production for water over a period of time is going to equal to that of the decomposition of hydrogen peroxide because they are equal to each other. And it's molar over hour, that is the unit. And for the rate of production for oxygen, it is 1/2. So over here, it is 1/2 of that of the decomposition of hydrogen peroxide. And therefore, it is going to be 1.60 times 10 to the negative 2 molar over hour. Remember that moles over liter is molar. The rate of formation for bromine is 6.0 times 10 to the negative 6 moles over seconds in a reaction described by the following net ionic reaction. Write the equations that relate the rates of consumption of the reactants and the rates of formation for the product. So we know that in this case, the rate for the consumption of the reactants is again negative because the reactants are decreasing in amount as the reaction proceeds. And so the negative comes from the fact that it's a reactant. And then the 5 is coming from the coefficient. And then the rate of bromide ion consumption. And that is the change in the concentration of bromide ion over a period of time. Same idea for the borate. So for borate, we can see that again, it is again a negative because it's a reactant. And then it's 1/1 because in this case, it doesn't have a coefficient. And it is the concentration of borate ion over a period of time. And that is equal to the consumption of protons, so hydrogen ions as well. So we can see that it is 6 because of that. And then again, the negative indicates that it is a reactant. So that is the rates of the consumption of the reactants. And then because we're using the same chemical equation, so it is equal to the rate for, we can also set it so that it can be expressed using the same equation for the rates of formation for the products. So the positive sign indicates that it is a product. And then the 3 again comes from the coefficient of the chemical reaction because we're looking at the same one. So that is again positive for the production of water. So coefficient as well as the positive sign.